So PI6, we are going to be using this equation. Now let's find the equation 6.116. That's this equation right here. And I'm claiming that you can just set up a line integral from the origin to a point in question of your vector field dx. And when you compute that line integral, that will give you a value that you're going to call the value of the function at that point, x naught. That was your upper bound. Okay. So let me go back here. So we've got our vector field. Let's see here, 3x squared, c squared, and 2yz. Okay, so I'm going to define my new function f at the point x naught to be, as required, integral from 0 to x naught of this field dot dx. And now it's just a matter of kind of writing this down. Now I've got to parameterize a path, right? And the path from 0 to x naught. And I'm going to do that in the most convenient way I can think of. Namely, I'm going to have x equal to x naught t. In other words, x, y, and z are going to be x naught t, y naught t, z naught t, which makes x prime, y prime, and z prime easy to compute. Those are just x naught, y naught, and z naught. And so then this turns into integral from 0 to 1. Note t goes from 0 to 1 here in that parameterization. So integral from 0 to 1, f, which is that, but keep in mind x is x naught t, and y is y naught t, and z, both of these z's here are z naught t. So let's write that down. I have 3x squared z squared 2y z, there's your vector field, dot x prime dt. I'm going to multiply this out. And let's see here. We're going to have 3 x naught cubed t squared plus, let's see here, y naught z naught squared t squared plus 2 y naught z naught squared t squared. Now this is an integral from 0 to 1 dt, and that's going to give you x naught cubed plus 1/3 y naught z naught squared plus 2/3 y naught z naught squared. Oh, and that's convenient. That's in fact these have the same. They're roughly the same. 1/3, 2/3. It adds up to x naught cubed plus y naught z naught squared. Does that make sense? So this is f of x naught. Now there's a little dummy variable discussion that I should give, and that is that, keep in mind, the reason that I defined this function in terms of x naught, right, is because I really needed to reserve x to be this describing the parametric curve that I was going to be using. But normally, of course, once you know the formula for a function, you can rewrite in terms of whatever variables you'd like. So let's let's do that. And I'm going to rewrite this function then as f of x equals x cubed plus yz squared. That makes sense? So this is just a brute force now. Of course, as you've observed already, I mean, sure, it's clear that this, the gradient of this function is equal to that. That's easily checked, and is equal to this. And of course, you could have found this function by taking this vector field and playing the anti-gradient game from 6.6. From earlier in this section. But here, the purpose of this problem was to show you that this construction that we used in this proof is actually valid. This really does find an anti-gradient. Yeah. Right. Cool. Everybody cool? Okay, great. So hang on a second. This was which problem? This was PI6. Okay.